So we're going to talk about light and the electromagnetic spectrum as a primer to talking about telescopes. So when we refer to light, what we usually refer to is what we're seeing with our eyes in our everyday life. And all we can see with our eyes is actually a very small amount of what we refer to as the electromagnetic spectrum. This is visible light. Visible light will have a wavelength, specifically from about 400 nanometers to about 700 nanometers. So these are very, very small wavelengths. So you can see with your eyes from the visible to about the red end of the spectrum. We actually experience the infrared end of the spectrum when we actually put up our hand and feel heat coming from the sun. So this essentially is heat radiation. We then have ultraviolet. This is the kind of wavelength that actually burns you and gives you things like sunburn. So, although we are sensitive as humans to ultraviolet and infrared radiation, this is all we can see with our eyes. And in the electromagnetic spectrum, there is much, much more going on than just what can be seen with the human eye. Very short wavelengths are very high energy radiation, very long wavelengths are very low energy radiation. So at this end of the spectrum, we have radio waves. At this end, we have gamma rays, X-rays, and cosmic rays. And all of these things can tell us something about how the universe behaves. So what is light? Light is electromagnetic radiation that moves in the form of what are called photons. And photons behave as both waves and particles. But fundamentally, electromagnetic radiation is a way of transferring energy from one place to another, and light itself is really just a combination of magnetic and electric fields that are varying with time. So here's what a photon would look like. It's really a magnetic and electric field that's interrelated and propagating through space. It's kind of a wave and a particle at the same time. So think of a photon as essentially a packet of waves. Now, when we talk about light, there is a very specific limit, and that speed limit is the speed limit of the entire universe. And the speed limit of the universe sits at about 3 times 10 to the 8 meters per second, or about 200 million meters per second, 299.7 times 10 to the 6 meters per second. So this is incredibly fast, but nothing in the universe can exceed this speed. And light, at least in a vacuum, will travel at exactly this speed. So when we talk about the light year, that's the speed that light is traveling. And that's how far the light year essentially says how far light will go in a year traveling at this speed. So this is a very high speed. And that really tells us why we don't have spaceships like we see in science fiction, where they go at multiple times the speed of light. The speed limit of the universe is about 3 times 10 to the 8 meters per second, and nothing goes faster than it. But that's the speed that light moves at in a vacuum. It will change speed in other media, such as air or glass or water, but generally 3 times 10 to the 8 is our accepted speed of light. Light has 3 basic properties. It has an intensity, a frequency, and a polarization. We're going to talk about what these mean and how we can utilize these in astronomy to tell us about objects in the universe. The intensity is how much energy you're receiving from your light source, and that relates to how big your wave is or what the amplitude of the wave is. A more intense light source has a higher wave and has a higher amplitude. So what we're really referring to when we talk about an amplitude is how high is the oscillation of a wave about a 0 point. So in terms of the amplitude, we would say how high is this wave? So amplitude is measured in meters. And if we had another wave that was even higher, that would have a higher amplitude and a higher intensity. So the height of this wave, if we were to study it, would be the intensity of the radiation. And intensity falls off as 1 over r squared. So think about shining a flashlight onto the floor and then shining it at a different angle. You'll see the same amount of light spread out over a much larger surface area. And that is the 1 over r squared rule. The further away you get from a light source, the lower the intensity, as the light is spread out further and further, with separation between you and the light source. So as you get further and further away from a light source, it's dimmer because the same amount of radiation is spread over a much larger surface area. The second value that we're interested in terms of light is frequency. And the frequency really tells you how energetic your wave is. It tells you how many times it's repeating itself in a second. And you often see this measured in hertz, which is a cycle per second, not a car rental company. And when you're talking about hertz, you can look at any radio dial, old-fashioned radio dial, and see that it will say things like 330 megahertz. Something like radio goes on about 300 million cycles per second, 600 million cycles per second. That's what a megahertz is. So 1 hertz is a cycle per second. And that cycle per second frequency is related to the energy of a wave. You don't need this equation, but quantum mechanics is needed to actually look at this equation and understand it and interpret it. So the energy of a wave can be thought of as how frequently is energy being delivered by that wave, and that is frequency. So energy, how much energy your wave has, is proportional to its frequency, how much energy is being delivered per unit time. So shorter wavelength means higher energy. That's what we really care about. So when we look back at our map of the entire electromagnetic spectrum, shorter wavelength equals higher energy. And energy is measured in units of joules. Really, that's just our general unit of energy for everything, including work and other concepts involving energetic systems. A watt is 1 joule per second. So when you buy a 60-watt light bulb, that light bulb is pumping out 60 joules of energy every second. So the frequency is related to the wavelength. The wavelength, if we look at our light wave here, is the distance from one peak to the next. And this will be in meters. For visible light, this is in the nanometers. That's 9 zeros, 10 to the negative 9 meters. So here's a bit of a summary. The things we've discussed here are frequency, wavelength, and intensity. The intensity, of course, was the height of our wave. So all of these 3 waves are of the same intensity. How high is this wave above some central 0 point? We then said our wave could have a wavelength, and that wavelength is related to the frequency. A longer wavelength gives you a lower frequency. And here's examples of cases where frequency is increased. So as you can see, if the frequency is higher, more waves are being delivered per second, per unit time. If you have a lower energy light wave, then you will have less waves delivered per unit time. So the wavelength is related to the frequency. The shorter the wavelength, the higher the frequency, the greater the energy. The last of our definitions was polarization. Now, you probably experienced this when you've dealt with things like polarized sunglasses, but sometimes people don't stop to think what this really means. But in terms of polarization, this describes the direction of oscillation in the plane 90 degrees to the direction of travel. What we're saying is when you look at light, it's actually very wild and very undisciplined and has lots of different waves all at different angles to one another. Now, if we take what's called a polarizing filter, which is essentially a transparent filter with lots of very, very fine lines on it, light can pass through that filter, and every light wave that is not oriented with the filter will be blocked. So here these lines move up and down. That means light polarized in this direction, up and down, can move through this filter. This is a nice experiment. If you then take another polarizing filter, turn it 90 degrees onto its side, this will then block the light entirely. And you could move these filters and you could allow light through or stop light entirely. And this is really why things like polarized sunglasses reduce glare. When we're looking at light, we're looking at light that is being transmitted to us in all of these various orientations. Polarized sunglasses have these polarized filters with very specific lines on them, which blocks all but a few wavelengths, allowing them through. All but a few wave orientations, I should say, allowing them through. And one of the things we can do in astronomy is use polarization to determine if light is being reflected or not. When we look at reflection, that changes polarization. So an angle of incidence is equal to an angle of reflection here. So this light wave is coming in and bouncing off. When the light wave hits this surface and bounces off, this could be a mirror, this could be water, this could be any reflective surface. When the light wave bounces off, it's polarized. So when we look at light from an object in the solar system or the universe at large, we can tell whether it's generating its own light or whether we're receiving light that is reflected, bouncing off of the object. A way of looking at polarization is if you actually look at a cell phone, probably a newer one than this. If you're wearing polarized sunglasses and you look at the LCD screen of a cell phone and you turn it sideways, sometimes you can see it turn black. So here we've got a phone. Put a polarizing filter between the phone and your eye, and then try turning your phone sideways. So try this with polarized sunglasses, and what you should see is at some angle as you turn the phone, the actual screen should go dark. When the screen goes dark, you've figured out the angle of the polarizing lines in your filter. So there's an experiment you can try for yourself. But in terms of astronomy, which is really what we're talking about, when we look into the sky, we see various things transmitting light to us. Now, if we take something like a star, this is actually generating its own heat and its own light as it's actually fusing hydrogen into helium and throwing out photons. Something like the moon or a cloud of inert gas will not generate its own light, but will have to rely on shining by reflecting light. So the moon, being very white and very bright, will reflect light to us from the sun. If we look at certain nebulae, the pink nebulae tend to be what are called emission nebulae, which are throwing out their own energy. These whitish silvery nebulae that you see, and a nebula is a cloud of gas that is floating in space, essentially stationary. A reflection nebula really only shines by reflecting light. Now, if we're to look at an emission nebula, one of the pink ones, we won't see any polarization. If we were to look at this nebula, this cloud of gas out in space, we would actually see that this light was polarized, telling us that this cloud is not very energetic and is actually just reflecting light. The dust and the gas of this cloud is reflecting light to us. And that tells us something about the nature of that region of the universe. So when we're experiencing light, light carries radiative energy. That's why sunlight feels warm. The infrared part of the spectrum especially is transferring energy from essentially from a wave into actual movement of molecules. So take your ice cream outside and put it in the sun, it will melt. So light is carrying energy from place to place. And if you go and lie out in the sun and you're out there too long, you will become sunburned, of course, as energy is translated to your body and reacts with it, causing thermal motions and causing burns. It's the UV end of the spectrum that tends to cause things like sunburn in humans. When it comes to light, humans are not particularly gifted. Goldfish can actually see a greater wavelength of light than humans. Not really sure what they do with that information, but they can see much further into the infrared and ultraviolet than we can. Sharks can't see things like magnetic fields, but can sense them, and they can actually navigate by electromagnetic fields of the Earth. So can creatures such as pigeons. An octopus is actually very advanced. The octopus eye actually has none of those floaters that humans get in it. This is due to the actual movement of blood around the eye rather than over it in an octopus versus a human. So octopus eyes have a much greater array of wavelengths than humans, and they are a little more advanced. Now, if we're talking about a star, let's pick on the sun. Something like the sun actually throws out radiation across the entire spectrum, radio wavelengths, gamma rays, everything. The sunlight is comprised of lots and lots of different wavelengths, but can be broken down into its component wavelengths for study. Our sun actually peaks in the yellow, even though this star is blue behind it, so you can still see the writing. Our sun, I should say, peaks at lambda, which is wavelength of 501 nanometers. So our sun throws out radiation of all different types, of all different wavelengths, but is peaking in the yellow. So remember, shorter wavelength equals higher energy. So as I said, the light we see is part of a whole electromagnetic spectrum, from radio waves through to the kind of microwaves you can harness to cook food, infrared radiation, visible radiation, X-rays and gamma rays. And with X-rays and gamma rays, they're so small, their wavelength is so short, and their amplitude essentially, that they can actually fit between the particles of solid matter. So X-rays and gamma rays can travel through walls, travel through people, because they are so small. And here's what we're talking about. Here's our wavelengths: short wavelength, long wavelength. Here's cosmic rays and gamma rays. This is all the high energy stuff, and this is all the low energy stuff. And we can use all of these different wavelengths to tell us about the universe. But this is what we experience with our eyes. This tiny little region here that is blown up so we can see it better. So we've talked about Newton before at length and some of his experiments. Newton was really the first person to document splitting up sunlight using a prism. So if we take a prism, which is essentially a triangular piece of glass, and then put it up to the sun, here Newton actually put up a very large blackout curtain and allowed a ray of light to come through his curtain, and then he put a prism in front of it. This actually causes light to be broken down as it's bent in two different directions. The sun entered this prism and he projected a rainbow effect here onto his chair. And this is the effect we're talking about. take a white light source and then put a slit here to make a fine beam, and then we can put a prism here, and the light will be refracted, that's bent once, then bent again. As this occurs, the speed of the light changes, and this breaks it down into its component wavelengths. And here we can see the entire spectrum of visible light. And this is how Newton confirmed that light was actually made up, that white light at least, was made up of all the other different colours combined. So what Newton did was take sunlight, put it through a prism, break it down into its component colours, and then put it through a second prism and recombine it to make white light. And that was how he proved that light was made of all different colours. So I realise this gets very Pink Floydy here, but this is essentially what he was doing. Here we've got light of all different colours coming in, recombined into white light, and then broken down again into our coloured spectrum. And this is referred to as dispersion. What's actually going on is our white light comes in, is bent, and all the different wavelengths of light start travelling at different speeds. As they travel at slightly different speeds, they all break up and they give us that pretty rainbow effect, proving that white light is combined of all those different colours. Another effect, one that we can use to great effect in astronomy, is refraction. Now take a pencil and put it in a jug of water, and that pencil will look broken. You have the same effect if you look at someone who's standing in a swimming pool. Quite often their legs look truncated and smaller, and they look a lot shorter than they actually are. The reason for this is as light travels through a different medium, it moves at different speeds. As it moves at different speeds, it bends slightly, and you see it at a different angle. So refraction changes the angle of the light you receive. This pencil is not broken, just that the light we're receiving from it, from the part that is submerged in the water, is coming to you at a different angle from the part that is in the air. And this is really useful, because if we know the density of different materials, that means we can bend light and put it to the place that we need it. So here, white light is shining onto this water, and it's being bent by the water, refracted by the water, and its path is being altered. If we can alter the path of the light, we can actually put the light where we want it, and sometimes even magnify it. And this is where refracting telescopes can be used. Here is an enormous refracting telescope. So here we have a large lens at the front. Light is refracted at the front, and it's magnified and then put through either a sensor or an eyepiece at the back here, where it's refracted yet again. So we can utilize refraction to magnify light from stars and faraway planets. Atmospheric refraction occurs quite a lot, and this will actually affect our view of the stars. If you think about something like the sun, if you watch a sunset, by the time the sun has actually set, the sun is physically below the horizon, but you can still see it. This is because the light is being bent by our atmosphere. So when you watch a sunset, the sun is physically not actually visible, but is down below the earth. But the light is bent around, and you are still seeing the sun go below the horizon. The other effect is that stars sometimes will twinkle. And you may notice this if you go out on a dark night and look towards the zenith, towards above your head. If you look in that direction, you'll see that stars probably twinkle less than those closer to the horizon. The reason being that stars close to the horizon are sending light through more atmosphere than those directly above your head. Consequently, the atmosphere itself is actually moving, and it's creating all these different little refractive indices, causing the stars to twinkle. The stars above your head are coming through less atmosphere, and are less susceptible to being affected by the atmosphere. Another effect is what's referred to as a mirage, and you can see this if you're driving on a particularly hot summer day. If you actually look around you, you can see that if you're watching the road, sometimes you see a reflection of the car in front on the ground. That's actually not a reflection, it's actually a refraction. And what this is caused by is, as we look at the road, the sun beats down on the surface and heats it up. That means that the air here is lower density than the air above it. This is hotter. At higher altitudes, the air is lower temperature. The higher temperature air is actually got a lower refractive index. So light travels faster through light down by the road than it does through air higher up. That means that light bends when it comes through the lower altitude air. Consequently, you can see an image of this vehicle down here as light from this vehicle is bending through the path of least resistance and bending through the low density air. So this is actually not a reflection that you see, but natural refraction. Now, light and solid matter can interact in a number of ways. When you shine light onto a solid object, it will either absorb that radiation, reflect it or scatter it. You also have what's called transmission, things like windows which allow light to move through them, or you can have emission. This is something that's actually putting out its own light, like a star or a light bulb. Sometimes materials will have a combination of several of these. So if we take something like a window, when you look through a window, you can see light coming through that window because you can see through it. Sometimes you'll even see your own reflection in that window. So some light is being scattered back to you. It's being reflected back. And some light won't make it through and will be absorbed by the glass and heat the glass. So here we have scattering, absorption, transmission when light comes through a material, and reflection when light bounces off a material. And here we have this particularly well-dressed man standing in quite a dull room. And in this particular case, light is being emitted. It's bouncing off very bright snow, which is an effect we see on other planets. And it's being absorbed by the dark ground. Light is coming through this window and bouncing off of him. His blue shirt is absorbing every wavelength of radiation except blue, which it is reflecting. The glass is transmitting light. This light bulb is emitting white light. This is an emission. And this mirror is reflecting all the wavelengths of light incident on it. Light is bouncing around this room and hitting this chair. This chair is red, so this chair is absorbing all the different wavelengths of light, all the colors, except red, which is reflecting back. So when we're looking at other planets, we can often talk about them in terms of albedo. Albedo is a measure of brightness of an object. High albedo is a bright object, low albedo is a dark. So take something like Mars, if we're to look at its polar caps. The low albedo stuff is essentially the rocks. The high albedo is the polar caps. So when we look at Mars, here we can see the bright polar caps very, very clearly as they're reflecting more radiation into space than the rocks around them. The rocks around them are absorbing radiation. If we're looking for life on other worlds, quite often plants form the basis of most ecosystems, and light can actually affect how life develops on a planet. So if we take something like plants, they're generally green. That means they absorb all wavelengths except green, and they're throwing away what they don't need to generate energy. So we're seeing what plants don't need. So they absorb all wavelengths except that around 510 nanometers, 510 billionths of a meter. So we talked about refraction. The other effect that's used a lot in astronomy and telescopes is reflection. And this essentially is where light bounces off an object. So take a reflective object and shine a light on it. You'll have what's called an incident ray, which is the incoming light ray, and then a reflected ray, which is the ray bouncing off of that surface. And the angle of the incident ray equals the angle of the reflected ray. And as we said, when we look at a nebula, we can tell from polarization whether light is being reflected here. And here we can also look at the angle that light is coming from, say, this star, and bouncing off of these molecules, this dust and gas in this nebula. Now this is a bit of a deceptive image. This is not space, this is not a hole in a nebula. This is actually material that's so dark that energy is being absorbed and cannot make it through. Here, this star is probably burning its way out of this nebula after being born, and then causing this nebula to shine as light bounces off of it and comes to Earth. And we can exploit reflecting the concept of reflection to make a telescope. We can use a shaped mirror to actually magnify light and bounce it to where we want. So a telescope like this utilizes light coming in, hitting a mirror at the back of this telescope, bouncing forwards, hitting another mirror, and then being reflected through this lens at the front to focus the light. This is a Newtonian reflector as put together by Newton. And here's Newton's original telescope versus this somewhat crude replica. Modern telescopes, like the one we have here at Gannon, are more like this, a Schmidt-Cassegrain type, where here light is incident through a small refractive plate, bounces off a mirror here, which actually magnifies the light, is bounced to a small flat mirror here, which then reflects the light back through an eyepiece and allows you to see a magnified image of the object of interest. So transmission, reflection, and refraction can be used to magnify light and study the object of interest. Emission, the one we haven't yet discussed, is anything which is giving out its own radiation. Things like light bulbs and stars are pouring radiation out themselves through heating up. If we take something like the sun, we are looking at hydrogen being converted to helium, which is releasing many watts of energy per second. If we talk about a light bulb, here we're talking either fluorescence due to electrical flow through the light bulb, or we're talking about, say, a wire being heated or an LED, which power passes through and causes the bulb to actually light. So when we look at emission, one of the things we can do is take the light from an object which is emitting radiation and break it down in very much the way that Newton was, but far more accurately than Newton did with his prism. If we do that, we can break the light down and we can actually identify the components of the particular object which is emitting the light. And we call this a spectrum. And a spectrograph is an instrument which breaks down the light from stars and planets and allows us to determine what materials were emitting that particular radiation. And we essentially can use spectra to tell us all about the chemical constituents of the stars, of the nebulae that we're looking at, and of the planets. And there's a typical spectrograph. Now, for scale, this is on the IRTF telescope in Mauna Kea in Hawaii. I took this picture while observing. Here's a gantry that a person would stand about this high on. Here's some oxygen bottles that are probably about 4 to 5 feet high here. So this is the size of one of these systems, and this huge C-clamp here is the mount for this telescope. So these are spectrographs. Light is coming through this telescope and then being broken into its component wavelengths, and the different wavelengths counted, and that tells us what the substance is that we're looking at. So a spectrum can actually be a fingerprint of a substance. Electrons that are in atoms that make up every type of chemical have distinct energy levels, and each chemical element, ion or molecule will possess a unique set of energy levels. And by breaking the light down and looking at those different wavelengths and determining the energy levels, we can actually look at these fingerprints of these different substances. So we can put our spectrograph on a star and say there's hydrogen, helium, lithium. We can say what makes up that particular star just by looking at its light. But a spectrum is actually a result of electrons in atoms moving up and down in energy levels. And the atomic mass and how heavy a particular element is determines its properties. And you can look through the periodic table, and looking at the spectrum from a star or from a planet or from anything that's giving out radiation, you can determine what it's made of. And a typical absorption spectrum, here's one of the star Vega, will look like this. So the atmosphere of Vega is actually absorbing some wavelengths of radiation, and that's what all these lines represent. These are all the places that light is being blocked as it comes out of the star. And that tells us the chemical constituents of the outer parts of the star. If we look at something like the sun, here's the sun, it has a hot interior and a cooler outer atmosphere, radiation will be blocked and give us these specific lines. This would be the spectrum of the sun if radiation was just being pumped out across the entire spectrum. The outer atmosphere of the sun here is blocking the radiation and giving us these very distinct black lines. Astronomers will know what wavelength these lines are, and that will tell us what the chemical species is that we're looking at. And there's the spectrum of the sun. Down here, here's the spectrum of the sun here somewhere. G, a G-type star. So here's the spectrum of the sun, very similar to HD 70178 here. This would be typical of the sun. And as you can see, the cooler the stars, which are these K and M stars, which we'll talk about later, the more lines of these dark lines they have in them. So those are typical spectra, and by looking at these spectra, we can identify the chemical constituents of each of these stars. So by the atomic structure of these particular items,